Hi, my name is Max Gede, and I'm your presenter for today's webinar on camera performance measurements and tests for the automotive imaging systems. First, a little bit of my background. I studied photo engineering at the University of Applied Sciences in Cologne in Germany, and during this time I began my career as a lab technician at image engineering. And so after graduating, I started working in the research and development department. That was around 2015. I led development projects for highly uniform light sources, and I joined the IEEE P2020 work group. And so over time, my focus shifted more and more towards automotive imaging, and I led the development of the first dynamic automotive imaging test stand. In 2021, I took on the responsibility of heading the newly formed Image Quality Lab and Innovation Department at Image Engineering, where we offer tailored image quality testing services to our customers. As you can see, the foundation for all testing is standardization. We are part of multiple standardization work groups and closely follow the development of imaging standards, often contributing our expertise to these groups. We are also aware of the QCT 1128 standard and support most of the measurements proposed in it. However, we view the upcoming IEEE P2020 standard as the main driver for qualification and validation work in the automotive imaging industry. Now, let's take a look at a typical process of qualifying components for a system and where image engineering might help. Usually, the manufacturers invest a lot of effort into qualification process, which often involves multiple iterations of requirements, testing efforts on the supplier side, and subsequent testing on the OEM side. The lack of trust in the industry tends to drive up the cost and effort required for qualification. We at IQ Lab of Image Engineering offer a truly neutral position in this setting. We can help both parties decrease time, effort, and associated cost of the qualification process. On the supplier side, we can help increase confidence that the product, this means the sensor or the lens or the whole system, is performing at its best. On the manufacturer side, we can provide neutral measurements that can be directly used as foundation for the decision-making process. Let's take a look at a typical camPAS test. First, we sit down with the camPAS client, in this case the system manufacturer, and define the exact test scope for the evaluation. This can include multiple image quality factors or key performance indicators, KPIs, depending on the use cases the imaging system is actually intended for. So, for example, if you're looking for front-facing ADAS systems, or if you're looking for camera systems that are in the camera band, the requirements definition would actually differ. So in this case, in this example, we examine the contrast transfer performance, CTA. We examine the flicker performance with MMP, modulated light mitigation probability, according to P2020. We examine the resolution with the Edge SFR as proposed in IEEE P2020, and the potential performance and color separation of the system. The camPAS test scene is used to link the numerical results to the subjective image perception. This helps even untechnical people to understand the numerical results in the report. So usually we source the components on the test, as we maintain close contact with the 5 largest automotive sensor manufacturers, and we are frequently updated on roadmaps, technologies, and software to these sensors. Bringing up the components is part of our service. We ensure everything works as expected and verify with the component suppliers. And once all systems are ready, we provide release images to all stakeholders involved in the test. And in the end, the camPAS client receives the camPAS report, a comprehensive document explaining the visualization or metrics. We will go over the key performance indicators in the next slides. In my personal opinion, contrast transfer accuracy, in short CTA, is one of the main KPIs when evaluating an image sensor. simply because it provides a broad overview of the system's performance in a really wide variety of situations. To understand how this works, we need to know that the camera can only detect objects if there is a non-zero contrast between the object and its background. With CTA, we present the camera system with a set of luminances and calculate the probability that the camera can differentiate between these luminances. The great thing about this method is that we can seamlessly jump between real-world scenarios as seen on the left and lab situations as seen on the right. To summarize the math really quickly on the bottom, each luminance perceived by the camera generates a distribution of digital values, as you can see on the right. We can calculate the contrast between these two distributions to determine the contrast transfer accuracy of the imaging system. The best possible result is a CTA of 1, and the worst possible result is a CTA of 0. We can map the results to different colors as seen here in the heat map on the right side, from 0 to 1, from violet to yellow. We can map then the different results for different luminance pairs on this heat map. Let's take a look at the axis. The x-axis shows us the average luminance of the luminance pair. The y-axis shows us the incoming contrast of the luminance pair. In color code, we see, as mentioned, the CTA performance. Now, we can map different situations to the heat map and also see different performances and look at situations and go back into the real world domain. Let's look at the example here. We have dark asphalt. We have a bright lane marking. This is a high contrast situation with mid luminance. So we would see this performance somewhere here where we have high luminance situation and a contrast which is not 0 but not like maximum high. Let's take a look at a situation with higher contrast, and this may be here. So we can see this is the headlight of the car, and this is the approaching car in front of it, which is pretty dark, which will give us high average luminance, but also really high incoming contrast. This works and shows us a really high contrast transfer accuracy. Now we can take a look at situations where we do not have a good transfer accuracy, but rather a low contrast transfer accuracy. In this situation here, I'm not sure if this is coming over a presentation, but there is a pothole on the right side. And we can see that this square is showing the pothole and the other square is not showing the pothole. So we have a low light situation here in the bottom, and we have a really low contrast. And we can see that the camera will not be able to transfer this contrast accurately. And so yeah, this is a typical situations where we can link the data to scenes and link the scenes back to the data. A typical setup that we will use in a lab to obtain the numbers for CTA is a setup made of 6 Vegas, which is called VLS for versatile light source. And we will present to the camera a situation where we have a luminance range or dynamic range of over 120 dBs. Typically starting somewhere around 50K candela per square meter and going as low as 0.05 candela per square meter. With this setup, we can generate the map that you have seen on the previous slide. Now again, what we do is we capture images at different temperatures. For example, here we have measured the camera at the sensor junction temperature of 80 degrees C. We measured the CTA for each color filter array. We can see that there is slight variation between the channels, but it's not that huge, which is expected. We also can generate directly in OECF, so it's the optoelectronic conversion function, and we can see if the channel ratios are linear over the whole range of luminances, which is often not the case. In this case, we can see, for example, that this is an HDR sensor and we have some kind of a drop here, where there is a misalignment between the channel ratios. Next is our setup for spatial frequency response. It is also, as mentioned in the IEEE P2020, we use IQ flat lights, so multispectral light sources, to generate various spectra and various spectral illuminance for the evaluation. We use the specified slanted edge chart from the IEEE P2020 standard, and we evaluate the E, so the edge SFR for this. Typical results would look like this. For different illuminance, we can see here the SFR 50 performance, for example, summarized for 5 lux at the chart, 200 lux and 2000 lux. Usually we test even lower numbers. We can go as low as 0.1 lux on the chart. This helps specifically in low light situations, which tend to be the most challenging for automotive imaging imaging systems. MMP is the modulated light mitigation probability. To understand this, we need first to understand what flicker actually is in images. Let's go through the basics really quickly. So if we have a modulated light source, it generates modulated light. If we capture this modulated light with a camera, with a rolling shutter, we will see banding artifacts in every image. Now let's take a look at one pixel in this image and take a look at the pixel value over the frames, saying over time. We will see fluctuation, which is caused by the banding artifacts. The digital value will go up and down. This is just for the linear case for single exposure. If we have some HDR exposures, and even if we have the ISP controlling the image, this will look even more chaotic. The digital values form a probabilistic distribution. And if we look at this probabilistic distribution here, we can see that the number, the performance KPI MMP, is formed as the area under the probabilistic distribution, which is determined by the mean value of the digital values and by the boundaries around this mean value. So all this area here is MMP. To understand this a little bit better, we can see here, for example, a system where the flicker mitigation turned off, and on the bottom, a system of flicker mitigation turned on. We send modulated light through the system, and we see on the top, as expected, digital values fluctuate. They go up and down with the banding artifacts, and we see that our MMP value is really small. It's nearly 0. If we take a look at the flicker mitigation on, as we see here, we see that there is only some noisy distribution, and we see that almost all numbers, all digital values are in the boundaries. Our MMP is 1. Analog to the CTA visualizations, we can put all the numbers we have obtained from the MMP analysis into a heat map. So yellow numbers or yellow color will show there is low flicker, and blue will show there is high flicker. On the x-axis again, we see luminance. So as we can see that flicker changes over the luminance, And on the y-axis here, we can show that we have tested multiple frequencies. We can see this is kind of an HDR sensor, at least 3 exposures. We can see it from here, and we see that the flicker performance varies with the frequency, and it varies also with luminance. This is a very important learning from this. Another learning would be if we change the duty cycle of the incoming light source. So for example, from going from a really short pulse of 10% duty cycle to a really long pulse of 90%, we see that the camera performs a lot better with a higher duty cycle, which is also expected. Cameras tend to perform worse with a really short pulsed light sources. We also see that the HDR nature of the sensor is getting a little bit lost in this 90% duty cycle scene. What we've done so far is generating values, generating results, generating numerical and visual results. Now, what we do now is we capture images at same or similar situations with a test scene that we developed specifically for camPAS, for camera performance for automotive systems. And what we can do with this is we can see the effects that we have seen in the numbers and link them to different artifacts that we can see in the images. We do this over a whole variety of different luminance levels. We can perform this also with multiple spectral illuminations, but the most effect comes from changing the overall illumination. As we see here, at some point, each camera will lose its peak performance and will go into a noise floor, and we try to find exactly this illumination level. The current test scene itself, in the current situation or in the current revision, consists of a background chart where we have a set of grayscales where we can literally just see the contrast getting lost. We see some dead leaves charts also at full and half contrast, and we see for visual evaluation, we see some grass patches and pebble patches. And as a reference, we have some darkly clothed mannequins and action figures in the scene also that we see on the left and on the right. They are called Alice and Bob. And for a true black reference tone, we have also some super black holes on the left and on the right. On the bottom, we see some repetitive textures that also tells us a lot about the about noise. Yeah, we can link a lot of the artifacts we see in these images to the actual artifacts we see in the numbers. What we also do, and not only with the testing scene, we do this with all contrast metrics, is we perform all the tests we do at different illuminations, but also at different junction temperatures. Here you can see a really good example of the temperature effect on the noise level and on the contrast loss of the sensor. You can see here, this is an image from a low light situation. If you'd ask me, I would say it's around about 1 lux of illumination on the chart. And we see here that the figure, so Bob, is still really well visible on the right side, and we can kind of see where the lines are between the single patches here. If we increase the temperature over and over again to reach 110 or even 120 degrees as required by most automotive OEMs, we see that the person in the dark is getting lost in the noise, and we also see that we cannot distinguish the contrasts here anymore. And the great thing is we not only test this with the camPAS scene as mentioned, we also test this with CTA, so contrast transfer accuracy, and we can precisely match the artifacts we see here in temperature degradation between the camPAS scene and CTA, and the CTA heat maps, yes. Everything you have seen so far in this presentation is related to ADAS testing, so image quality system for exterior of the car. We also have some efforts in in-cabin testing, specifically in the region of RGB IR or IR only testing. We developed a small program of combined test scenes where we use mannequin heads and also different test charts to determine the image quality of RGB IR systems. RGB IR systems are usually used in the driver monitoring systems or occupancy monitoring systems, or even some in-cabin entertainment systems. And so what a typical test case would be is the upscaling functionality of the IR or the upscaling functionality of the RGB. Using the image engineering IQ floodlights as illumination, which are multispectral light sources, we can generate our own spectra to our liking. So for example, in this case, we generated D65 on the left, and then we just added the near infrared to the D65, and we have obtained information of the color fidelity or color transfer, color rendering of the sensor, which has shown some downfalls when adding infrared, as you see in this image. Analog to the ADAS tests, we of course also test spatial frequency response, also ESFR. In this case, we can choose if we use the passive case where we illuminate on our own, as for the ADAS case, or as in this case, we use the built-in big cell or IR illumination from the DMS system itself, which shows a rather different performance than with our own illumination. To generate relevant data, we discuss and define testing positions, which can be related to the actual position of the camera in the system and typical head positions in the car. You can see it on the right. To test typical KPIs like the optoelectronic conversion function, dynamic range, and signal-to-noise ratio, we use Image Engineering's LE7 IR device. As already mentioned, we can generate with the IQ-LED our own spectra. We can generate custom spectra, we can generate standard D65 spectra. But what we also can do is we can generate a spectrum which is typically used in the infrared in the automotive environment of 850 or 940 nanometers. This slide is just for reference. This is how a typical photo would look like, and on the right you see typical results from an OCF or an RGB IR camera. The light source used is the LE7 as mentioned, and we used in D65 extended IR spectrum. As driver monitoring systems are often used to track the eyes of the driver, we have developed our own eye contrast test chart, which consists of cobblestone targets at different contrasts. We illuminate typically this test chart with the interior active illumination and capture different images. Here's some examples. We have captured the images at the previously mentioned test positions, as you can see here. And as you clearly can see that at some point, at some contrast, the cobblestone target in the middle is not visible anymore. This can be seen with the naked eye, and this can also be calculated with different metrics. At last, I would like to thank you for your attention throughout the whole presentation and summarize what we have explored. So first is the importance of sensitization, of course. It's also the process of qualifying components and the critical role of different KPIs. We have learned something about CTA, contrast transfer accuracy, about MMP, modulated light mitigation probability, the testing devices we use for ESFR measurements, and the camPAS test scene. We also have learned that temperature testing is a crucial part of testing for automotive imaging. And we have learned that at Image Engineering, we're committed to providing precise, reliable, and unbiased testing services. I would like to thank you for your attention. If you have any questions or would like to discuss further, please feel free to reach out. We look forward to collaborating with you. And yeah, reach out to Test Lab at Image Engineering or directly to Leon Chow. I'm looking forward to your questions. Thank you very much.